Right, morning year 12, just a quick one from me. You're going to continue with your mean and standard deviation questions. There will be some extra reading for you to do that I'm not going to cover today in this video. But what I will cover is mean and standard deviation of coded data, and I'll try to explain what that means, and also mean and standard deviation of group data. So what coded data is basically you've got some original values. These are your X numbers, your X values, your original bits of data, for example. So let's actually do this first without even a question. So the question, or how it might start out, would be something like this. I'm going to have my X values, this is my original data. And I might have something like, here are the numbers. So 5, 7, 9, 9, and 12, right? And so we can work out X bar, and we can also work out the standard deviation. Now, I'm going to put a little subscript X to indicate the fact that this is for the X values. So we can actually work this out. So let's work this out. So X bar is, let's work this out, 5 add 7 add 9 add 9 add 12 shared by 5, so this is 8.4. What I'd like you to do is pause the video and see if you can work out the standard deviation. So I'll give you 2 seconds to pause the video. Right now I'm going to go through it. I fully expect you to have actually paused the video and spent however long it takes you to work out a standard deviation. I'm going to go through this now. So what you want to do is you want to square all of these. I'm going to use the more simple, kind of, in my view, easier to use version of the formula, which is to sum up the x squareds, divide by how many there are, and then take away the mean squared. And of course, if I want the standard deviation, I'm going to have to square root that. So for us, this is the formula we're going to use. That's what I'm going to use anyway. If you've used the other version of the formula, that's fine. Let's just hope you get the same answer that I do. So what I want to do is I want to add up all of these things squared. So 5 squared add 7 squared add 9 squared, add 9 squared, add 12 squared, and divide by how many there are, which is 5. And then I'm going to take away 8.4 squared. Right, that's that X bar getting squared that I have to take away. And then I will square root this answer and get 2.33. So you should have the original sigma is about 2.33 to 2 decimal places. Okay, so we can work these things out. I'm just going to maneuver the calculator here and make it a bit smaller. Right, now what does coded data mean? So this is where I'm now going to affect the X numbers by a linear transformation. So what that means is I'm going to times all of the numbers by something and add something. So I'm just going to do an example. I'm going to do the same example. Well, actually, this example here, which was originally here, was I was going to times all of the numbers by 3 and then add 2. Okay, that's what I was going to do. Let's do a different one. Let's do double all of the numbers. So there's a button on my pen here that if I accidentally press it, starts doing that. It's kind of annoying. Let's try again. So I'm going to double all the numbers and then take away 1, right? That's what I'm going to do. So the question is what effect will that have on the mean, and what effect will that have on the standard deviation? So I'm actually going to do this manually first, and then I'm going to talk about the reasoning behind it and how we can do this in general, right? So I am actually going, what this effect actually has is each of these numbers I'm going to double and then take away 1. That's what's going to happen. So 5 doubled is 10, take away 1 is 9. 7 doubled is 14, take away 1 is 13. 9 doubled is 18, take away 1 is 17. And then 12 doubled is 24, take away 1 is 23. And so what we actually have here is now y bar and sigma y. Okay, this here is my coded data. This is what this is. It's like I've got my original data, which is all the x numbers, and then I have done a linear transformation to it, which is something of this form, right? mx plus c, right? In any case, let's actually work this out manually and then see if we could have done it a different way, right? That's the idea. So let's do y bar first. So 9 add 13 add 17 add 17 add 23 shared by 5 is 15.8. So a question that I will ask in a moment, but you could start thinking about it, is what has happened to this 8.4 to produce this 15.8, and does that maybe make a bit of common sense as well? So we'll talk about that in just a moment. Let's actually do this first, and then sigma y. Again, I would ask you to pause the video and work this out for yourself manually. Right, now I'm going to go through it. Now this time round, I'm going to use the other version of the formula, because why not? I have 2 choices, and that's what I'm going to choose to do this time round. So this time round, I'm going to do sigma y. There's not a right or a wrong, but the idea is you have to be able to do both, right? You have to know both. So what I'm going to do this time is I'm going to add up all of the squared deviates or deviations squared and divide by how many there are. Okay, so I'm going to do oh, and of course I need to square root this. I need to square root my final answer, right? So let us work this out. So on my calculator, I'm obviously going to be dividing by 5 right at the end, and I'm going to have 9, well, we need it in brackets, I suppose. 9 take away 15.8 squared. Okay, close the brackets first and then square it. So this is 9, this take away the mean and then square it. Add 13 minus 15.8 squared. Add 17 minus 13.8. I'm writing the right thing in no 15.8. So you've got to be very careful. This is why I prefer the other version of the formula, because it's less to write on the calculator. Plus that again. So if I'd been being very efficient, I would have just put a 2 in front of that first bracket there. And then finally 23 minus 15.8, and then square that. And then square root this answer, which is 4.66. 4.66 to 2 decimal places. If I'd used the other version of the formula, what would I have to do instead? I'd have done 9 squared, add 13 squared, add 17 squared, add 17 squared, add 23 squared, all over 5, and take away 15.8 squared, and then square root that, get the same answer, right? So these 2 versions of the formula, both are going to obviously output the same answer, and you do need to know both versions of the formula, okay? In the last video, I actually showed you how these 2 formulas were in fact equivalent and how you could get one from the other. You don't need to know why they're equivalent. You don't need to understand that algebraic manipulation that I did, but it is there for anyone who's interested. Right, so anyway, let's have a look at this. What is the relationship that we've got going on here. This 8.4, what's happened to make it 15.8? Well, what we've really done is we've doubled this mean and then taken away 1. Okay, so if I do 8.4 and double it and then take away 1, I get 15.8. So what we can say is that y bar would have been 2 lots of x bar minus 1 for us here, right? For us here. And that should make sense intuitively. Oh, let me get rid of the calculator, sorry. There you go. That should make a bit of sense intuitively, right? If you imagine what's the average, what's the mean, if I double all of the numbers and then take away 1. Well, the mean, the original average, the original sort of midpoint, as it were, is going to double in value. And then if I take something off or add something on, it's just going to shift the mean up or down, okay? So the effect it has on the mean is it's going to double and then take away 1. Okay, if there was no doubling that took place to start with, maybe it was x adds 7 or something like that. All that's going to do is make the mean value 7 more. That is the effect that it has. And if you're not convinced, you could try this out with a bunch of different options, right? For example, here are 3 numbers, 1, 2, and 3. You tell me the mean. So you do 1 add 2 add 3, which is 6 divided by 3 is 2. So the mean is 2. If you now add 7 to all of these original numbers, you'll have 8, 9, and 10. Now if you add all of those up and divide by 3, you'll get 9, which is 7 more than 2, the original mean. The effect it has is it just does the linear transformation to the mean itself. Okay, that's the effect that it has. What's the effect on the standard deviation, which remember is a measure of how spread out the data is? What is the effect on the standard deviation? 2.33 certainly looks as though it's just doubled, right? Which potentially has come from this here. Let's click on there, sorry. The 2.33 has doubled to 4.66, and if you actually look back to the original exact values, you'll see that it was exactly double. That looks to me like it's come from this, but why is the minus 1 not affected the standard deviation? That's the question. Well, this time round, when we're talking about spread, or how varied the data is, if I ask you how spread out are the numbers 1, 2, 3 versus how spread out are the numbers 7, 8, 9, they're the same amount spread out. The range is the same. The interquartile range would be the same. The standard deviation, which is a measure of spread, will be the same. So if you shift data up or down the same amount for every number, if you add 20 to all the numbers, you make I'm mirrored in the camera, so I need to like go this way, right? So if this is where the data originally is, and I now add 20 to everything, all the data gets shifted up the same amount. I've not made my hands any wider. Okay? The original mean will get bigger, but the standard deviation won't get bigger if all you're doing is adding or subtracting the same number from every data point. However, if I double all the numbers, then this value here is going to get a bit bigger. This value here is going to get, well, they're all going to get twice as big. The gap between the biggest and the smallest will become twice as big. Okay, if you think about the maximum versus the minimum, you're doubling the maximum, you're doubling the minimum, you're doubling the difference between them. So the range would get twice as big, the interquartile range would get twice as big, and the standard deviation, which is another measure of spread, will get twice as big. The minus 1, or any additional subtraction after the doubling, will not affect how spread out or varied the data is. The only thing that affects is the mean. Okay, the only thing that affects is the mean. So for us, this is sigma y is 2 lots of sigma x. Okay, the -1 does not affect anything. So let's look at this one, this example question. So we've got a bunch of x numbers that we actually aren't even told, but we are told the mean of them is 7 and the standard deviation of them is 4. And we're told that we've got like coded data, which is we've taken the original data times by 3 and then added 2. So the question is what effect does that have on the mean and what effect does that have on the standard deviation? So the effect it has on the mean, so y bar will be 3 lots of x bar plus 2, and the standard deviation will just be 3 lots of the original standard deviation. Okay, the plus 2 doesn't come into it. And it's at this stage, perhaps I should have mentioned it before, but it doesn't matter too much. It's page 239 in your book, page 239, where there's this little bit of information here written in your book, that if y is ax plus b, then y bar, it affects the mean in the way you expect, but it affects the standard deviation only through multiplication by a. Okay, it does not have any effect if you add or subtract anything, because it doesn't affect how spread out it is. So I'm literally applying these formulas here. So for us, y bar will be 3 lots of 7, which is 21, right? Because it tells me here 3 lots of 7 is 21, add 2 is 23. And sigma y will be 3 lots of 4, right? 3 lots of 4, which is 12. Okay, so there are some questions in the book which relate to this, and I obviously need you to know what to do. Okay, so oh gosh, this has been 17 minutes of talking about one thing. Right, let's hope the next part is even faster. Okay. Hopefully you remember, so this is mean and standard deviation of grouped data. So mean of group data, that's GCSE. You would find the midpoint, which would be, I guess for here would be 7.5, for here would be 8.5, for here would be 9.5. This is not a very good example, but you get the idea. You just go to the midpoint. And of course, these are actually estimates, aren't they? And what you then do is you do 3 times 7.5, so you do the midpoint times the frequency. So I guess we've got some calculator work to do. 7.5 times 3, 22.5. 8.5 times 10 is 85. 11 times 9.5 is 104.5. 7 times 10.5 is 73.5. And what's that? 33 add 1.5 is 34.5. And then do you remember that you would add these up, because this is saying you've got 3 7.5s, 10 8.5s, 11 9.5s, 7 10.5s, and 3 11.5s. So this here would be your grand total, and you would divide by how many numbers there were. So 3 add 10 is 13, 24, this is 10, so this is 34. So you've got a total frequency of 34, and you've got a total midpoint times frequency. So this is where I have to add some numbers up. So this is just recap from GCSE. This mean question here is just a GCSE question. It's 320 that goes there. So my estimate of the mean is 320 over 34. Okay, which we could simplify. We don't want to, because we actually want to leave it as an exact value, because we're going to use it as part of the standard deviation calculation. I would not round it till the end, right? That's the idea. So this is 160 over 17. Okay, and you want to leave this exact at the moment. Now, how are we going to do our estimate of the standard deviation? So this is the A-level part, right? Well, the estimate of the standard deviation is I'm still going to do the kind of the same idea, except I'm going to have these midpoints squared, and there's going to be 3 of those that have been squared. There's going to be 10 of those that have been squared. So there is actually a formula in your book which I will copy and paste. Hopefully it's somewhere easy to see. Is there a formula in the book? I would have thought there should be. Okay, it's basically wants you to just do it manually then. Okay, well that's fine. If you want to be thinking about what's the actual calculation for the standard deviation, right? You want to be adding up all the x's squared and dividing by how many there are, and then taking away the x bar squared. So for us, this is going to be 3 lots of 7.5 squared, because this is the 7.5 that I need to square, and there's 3 of those to add up, plus 10 lots of 8.5 squared, plus 11 lots of 9.5 squared, plus 7 lots of 10.5 squared, plus 3 lots of 11.5 squared. That is all the squareds getting added up, right? That's the idea. Divide by how many of these things are there all together? Well, there's 34 of them. It's like a shorthand way of saying there's 7.5 squared plus 7.5 squared plus 7.5 squared, 3 of them, plus 8.5 squared plus 8.5 squared plus 8.5 squared plus, and there'll be 10 of those, etc. Right? So altogether, there's 34 of these things that I'm adding up, and then I will need to take away 160 over 17 squared, and then there'll be a square root of this absolute monster. So this is, you know, it's not the nicest. There's so many places to make a mistake, but you just have to persevere with it, basically. So let's type this entire thing into the calculator and see what we get, and see if we get the same answer as the book. So we are doing 3 lots of 7.5 squared. Again, I will say this one more time. It's because we're adding up all of the squareds, all of the data points squared. There's 3 of those 7.5 squareds. Okay, don't get confused. You're not squaring the 3. The 3 is telling you how many there are. You don't square that. 10 lots of 8.5 squared. 11 lots of 9.5 squared. And this, again, it's an estimate, remember, because the 9.5 and the 8.5 and all of these were our best guess at what these data points are. They are actually all spread out across 7 to 8, 8 to 9, 9 to 10, 10 to 11, and 11 to 12. So that's why it's an estimate. And then what? 3 lots of 11.5 squared. All over 34. And then I've got to take away the x bar squared, which remains our best estimate of the mean, right? This 160 over 17 is our best estimate of the mean, so we're going to use this as part of our estimate. This, by the way, kind of compounds the error. This standard deviation is now even less of an accurate estimate because we're having to utilize something within it that was itself an estimate. But anyway, it is our best guess. So we're going to press equals, and we're going to get 1.09 to 2 decimal places. And it's at this stage I would look to the book and cross my fingers that they have 1.09 as the answer to this. Oh, wonderful. Yes, look, it's here. There you go. 1.09 it is. 1.09 it is. So that was located on page 238. Right, in terms of what I'd like you to do this lesson, well, I'd obviously like you to try very hard to digest all of this information and basically do the rest of exercise 9.2a. When you finish that and you're confident with that, and of course I will be on Teams for you to ask questions. I haven't had any questions yet so far, so it must be, this all must be relatively straightforward, otherwise I would imagine there should be some questions. When you are finished and you are happy, you may begin reading the bit that comes after exercise 9.2a, which talks about outliers. So it's not that complicated. That does not need its own video. Pros and cons of the different statistics doesn't need its own video. And then you can begin exercise 9.2b, which again, I'm happy to help you with, and if you have any questions or there's any specific things you actually want me to go through, you let me know. Right, that's a 26-minute video, give or take. Have a nice day. Bye-bye.